In this and the next video, I want to work through a detailed example showing how a neural network can compute a complex nonlinear function of the input. And hopefully this will give you a good sense of why neural networks can be used to learn complex nonlinear hypotheses. Consider the following problem where we have input features x1 and x2 that are binary values, so either 0 or 1. So x1 and x2 can each take on only one of two possible values. In this example, I've drawn only two positive examples and two negative examples, but you can think of this as a simplified version of a more complex learning problem where we may have a bunch of positive examples to the upper right and the lower left and a bunch of negative examples denoted by the circles. And what we'd like to do is learn a nonlinear decision boundary that maybe separates the positive and the negative examples. So how can a neural network do this? And rather than using the example on the right, I want to use this maybe easier to examine example on the left. Concretely, what this is really computing the target label y equals x1 xor x2, or actually this is actually the x1 xnor x2 function, where xnor is the alternative notation for not x1 or x2. So x1 xor x2, that's true only if exactly one of x1 or x2 is equal to 1. It turns out that the specific example I'm going to use works out a little bit better if we use the xnor example instead. These two are the same, of course. It means not x1 xor x2, and so we're going to have positive examples if either both are true or both are false, and we'll have that's y equals 1, and we're going to have y equals 0 if only one of them is true. And we want to figure out if we can get a neural network to fit this sort of training set. In order to build up to a network that fits the xnor example, we're going to start with a slightly simpler one and show a network that fits the AND function. Concretely, let's say we have input x1 and x2 that are again binary, so it's either 0 or 1, and let's say our target labels y are is equal to x1 and x2. This is a logical AND. So can we get a one-unit network to compute this logical AND function? In order to do so, I'm going to actually draw in the bias unit as well, the +1 unit. Now, let me just assign some values to the weights or the parameters of this network. I'm going to write down the parameters on this diagram, right? -30 here, +20, and +20. And what this means is that I'm assigning a value of -30 to the value associated with x0, there's this +1 going into this unit, and a parameter value of +20 that multiplies into x1, and a value of +20 for the parameter that multiplies into x2. So concretely, this is saying that my hypothesis h of x is equal to g of -30 plus 20x1 plus 20x2. So sometimes it's just convenient to draw these weights, or draw these parameters up here, in the diagram of the neural network. And of course, this -30, this is actually theta 1 of 1, 0. This is theta 1 of 1, 1, and that's theta 1 of 1, 2. But it's just easier to think about it as associating these parameters with the edges of the network. Let's look at what this little single neuron network will compute. Just to remind you, the sigmoid activation function g of z looks like this. It starts from 0, rises smoothly, crosses 0.5, and then it asymptotes at 1. And to give you some landmarks, if the horizontal axis value z is equal to 4.6, then the sigmoid function is equal to 0.99. This is very close to 1. And kind of symmetrically, if it's negative 4.6, then the sigmoid function there is equal to 0.01. This is very close to 0. Let's look at the four possible input values for x1 and x2 and look at what our hypothesis will output in that case. If x1 and x2 are both equal to 0, if you look at this, if x1 and x2 are both equal to 0, then the hypothesis will output g of negative 30. So it's going to be very far to the left of this diagram, so it'll be very close to 0. If x1 equals 0 and x2 equals 1, then this formula here evaluates to g, that is the sigmoid function applied to minus 10. And again, that's to the far left of this plot, and so that's again very close to 0. This is also g of minus 10, that is if x1 is equal to 1 and x2 is 0, this is minus 30 plus 20, which is minus 10. And finally, if x1 equals 1, x2 equals 1, then you have g of minus 30 plus 20 plus 20. So that's g of positive 10, which is therefore very close to 1. And if you look in this column, this is exactly the logical AND function. So this is computing h of x is approximately x1 and x2. In other words, it outputs 1 if and only if x1 and x2 are both equal to 1. So by writing out our little truth table like this, we managed to figure out what's the logical function that our little neural network computes. This network shown here computes the OR function. Just to show you how I worked that out, if you write out the hypothesis, you find that it's computing g of minus 10 plus 20x1 plus 20x2, and so if you fill in these values, you find that that's g of minus 10, which is approximately 0, g of 10, which is approximately 1, and so on. And these are approximately 1, and approximately 1, and these numbers is essentially the logical OR function. So hopefully with this, you now understand how single neurons in a neural network can be used to compute logical functions like AND and OR and so on. In the next video, we'll continue building on these examples and work through a more complex example. We'll get to show you how a neural network now with multiple layers of units can be used to compute more complex functions like the XOR function or the XNOR function.